In the first part of 7.4, we talked about using a geometric power series to model or represent a function and how those two things are equal over some interval of convergence. And in today's lesson, we're really going to build on that. So we're going to look at some pretty simplistic examples, but the purpose behind that being that we understand at a base level how to do this or how to extend on this so that when we get to more complicated problems, we can use that same basic reasoning. So let's start with sort of a little warm-up. If f of x was equal to 1 over 1 minus x, then what would f of x squared be? So this is really, I could ask my Algebra 1 students this question. Hopefully they could answer it. They would say that this would be 1 over 1 minus x squared. So just using direct substitution to plug in x squared for f. Sorry, to plug in x squared for x. What if it was the square root of x? Then this would be the same thing as 1 minus the square root of x, or 1 over 1 minus x to the power of 1/2. And let's review last lesson a little bit more, and I'm going to have you go ahead and pause the video and write the power series for f of x equals 1 over. Actually, I'm going to have you change this. I want you to write the power series for 1 over 1 plus x, 1 over 1 plus x. Sorry about that. Go ahead and identify a and r and write that power series out. Write the first 4 terms and the general term. Then unpause the video and see how you did. And here we have it. Our first term would be 1, and since I changed that series to be 1 over 1 plus x, our r value would be negative x. So our series is going to be 1 minus x plus x squared minus x to the third plus dot 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 plus negative 1 to the n x to the n plus dot dot dot. So if that is the power series for 1 over 1 plus x, how would that be different if it was 1 over 1 plus x squared using the same logic that we used up here? Well, this would be equal to 1 minus, instead of x, it's going to be x squared, plus, instead of x squared, it's going to be x squared squared, or x to the 4th, minus x squared to the 3rd, plus dot dot dot, plus our general term, which is negative 1 to the n, x to the 2n plus dot dot dot. And you could simplify that to be 1 minus x squared plus x to the 4th minus x to the 6th. That's totally fine, but for the purposes of right now, I just want you to see how this pattern is changing. Go ahead and pause the video and do the same thing for 1 over 1 plus the square root of x. Then unpause the video and see how you did. And here we have 1 minus x to the power of 1/2 plus x, or plus x to the power of 1/2 squared, minus x to the 3/2, or minus x to the power of 1/2 to the 3rd, plus dot dot dot, negative 1 to the n, plus x to the 1/2 n. And then again, that is continuing on forever. And now we're going to build on this a little bit more, and I'm going to do 1, and I'm going to have you pause the video and work on 2 afterwards. But using exactly the same idea, thinking about g of x here, how could we use what we have just been doing to write a power series for g of x? So again, think about what a is, think about what r is. A is 1, r is negative x. So you could go about this the same way that we did last class. However, we already defined what this power series is, 1 over 1 plus x. We already defined that up here. So instead of starting from square one and using the geometric way that we did last class, I want you to think, what really is the difference between g of x here in number 1 and this function up here that we already did? So what is the difference? What's happening to make this series different? And what's happening is we're taking x and we're multiplying it by f of x. And that is this f of x defined up here, which means to make a power series, we could just take x and we could multiply it by the power series that we had for f of x. And I'm going to leave off the general term right now, just I think you kind of get the gist there. So that means that we could really say that g of x is really equal to x minus x squared plus x to the 3rd minus x to the 4th plus dot dot dot. And again, we could write a general rule in there if we needed to, but I just want you to see how we can use a power series that we already identified and build on that based on what is happening to that. So in this case, we're multiplying x by this power series that we already defined as f, x times f of x. So go ahead and pause the video and work on number 2 and see if you can figure out how h of x is possibly a manipulation of f of x, or a manipulation of anything else that we've already done on this page. All right, so I'm going to go ahead and define this function up here as k of x, since that's really close to what we're doing. And we could use a manipulation of f of x as well, but we can say that h of x is equal to x squared times k of x, or we could say that it's equal to x times f of x squared. So there's 2 different ways that we could represent what's going on in this particular power series. We could say that we're just taking this one that we already defined here, which I'm going to call k of x, and multiply it by x squared, or we could take the same one that we used in number 1, f of x, we could plug in x squared and multiply it by x, which I guess means we could also write this a third way. We could say that this is g of x squared. So actually, let's do that. Let's take the g function that we defined in number 1, and let's just directly substitute in x squared for each of those x's. So that would give me x squared minus x squared squared, or x to the 4th, plus x squared to the 3rd, or plus x to the 6th, minus x squared to the 4th, or minus x to the 8th, plus dot, dot, dot. So you might be thinking, what we're talking about right now is kind of cool, how we can manipulate one function or one series looking at how it relates to another function or another series, but we haven't really found a way to say, wow, this is incredibly helpful. I don't think I've proven to you that this can be incredibly helpful. So what I want you to do real quickly, just freshen up on our basic differentiation skills. I want you to go ahead and take the derivative of the function 1 over 1 plus x squared. You're going to have to use a little bit of the quotient rule there, or the power rule, depending on how you write it. Go ahead and take the derivative of that. And that should give you negative 2x over 1, the quantity 1 plus x squared, quantity squared. And yes, that was not an incredibly difficult derivative to take. However, what I'm about to show you is that what if this was originally our series, or if this was originally the function we were looking at? We can't write this as a geometric power series. There's no way for us to write this in the form a over 1 minus r. And because it's not geometric, that means that as of this moment, we don't actually know how to write a polynomial representation of what it is, and we love polynomials. We know we want to work with polynomials. So with the tools that we have, we can't write this as a geometric power series, but we do know the power series for f of x. And, this is a big and, we can find, or we know, the interval of convergence for the power series, which means that we can actually take the power series and take the derivative of that to find the derivative of our new function as a series. So let's go ahead and write our f of x as a series first. So here we have f of x, which is 1 over 1 plus x squared, which we've already worked with today, and we said that that is equal to 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th plus dot, 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 which means now we're representing this using a polynomial. Well, we know how to take derivatives of polynomials, so we could represent this series as the derivative of f of x. That means we could write this as, well, the derivative of 1 is 0. We could take the derivative of each individual term. X squared is negative 2x, 4x cubed minus 6x to the 5th plus 8x to the 7th minus dot, dot, dot. And then we can even take the derivative of our general term. Now remember, we're taking the derivative with respect to x, so negative 1 to the n isn't going to change at all, but the general term, x to the 2n, we're going to use the power rule, so 2n times x to the 2n minus 1. So we can even take the derivative to get a new general term for our series. All right, I'm going to have you go ahead and use what you know about derivatives to take the derivative of this practice number 3. go ahead and take the derivative of each individual term and the general term, and then see if you can come up with any ideas of what this power series might actually, what function it might represent. So go ahead and pause the video. All right, let's take a look at this guy. So f prime of x is going to be equal to 0 plus 1 plus 2x over 2 factorial plus 3x squared over 3 factorial plus 4x to the third over 4 factorial plus dot 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 plus n times x to the n minus 1 over n factorial plus dot dot dot. And let's go ahead and clean this up a little bit. So this is really f prime of x is 1 plus, well, 2x over 2 factorial is just x. 3 and the 3 factorial are going to divide out. So this is plus x squared over 2 factorial. Plus the 4s are going to divide out in this next term. So that's going to give me x to the third over 3 factorial plus dot dot dot. Plus the n's are going to divide out. So this gives me x to the n minus 1 over n minus 1 factorial plus dot dot dot. Now, if you haven't already, pause the video and see what you notice about f of x in comparison to f prime of x, and if that means anything to you, and if that helps you identify what function is f of x. So pause the video if you haven't already and stop and think about that. Okay, I'm hoping that what you noticed is this and this are the same. The only slight difference that you could argue looks slightly different is that here I have x to the n minus 1 over n minus 1 factorial, but really we just took the derivative, which means we started with n equals 0 for f prime, as opposed to starting at n equals 1 for f. So really, these two things are the same. So what did I just say? I just said that oops, I don't want to be in highlighter mode still. I just said that f of x is equal to f prime of x. Well, that's weird. And there is absolutely only one case for which this is true, and that is e to the x. Now, it's okay to stop and think, wait a second, what? What we're saying is that e to the x is actually equal to this series. That we could represent something as weird looking as e as something that almost looks like a polynomial. And the reason that we know that we can do that is because the original function and its derivative are equal. And that is super duper cool. And it's okay to admit that you think that this is super duper cool. Because if you don't, you're just lying to yourself. Our nerdiness levels think that this is super cool. We just figured out that this polynomial looking expression, this power series, is equal to e to the x because its original function is equal to the derivative, and the only time that happens is with e to the x. I'm sorry if I'm nerding out on you a little bit too much right now. I just think that that is such a cool thing that we can represent e to the x in this different way, and how we discovered that this was in fact e to the x. So let's move on now to talk a little bit about integrating with power series, since we just talked about differentiating with it. So you may be thinking that we just figured out probably the coolest thing we're going to figure out all year, and that might be a downer, that we just discovered a polynomial-like version, a power series version of e to the x. But fear not, we will do more cool things this year. In fact, we are going to do something cool right now. We are going to use a power series to, instead of creating something like e to the x, we're going to create something that, in my opinion, is a little uglier to work with than e, and that is natural log. So let's look at this for a minute. We know that the integral of 1 over 1 plus x dx is equal to natural log of the absolute value of x plus 1 plus c. Now, we also know that this power series, 1 over 1 plus x, where a is 1 and r is negative x, can be written out like this. For all x, absolute value of x less than 1. And that's just for our interval of convergence. We can say that 1 over x is equal to this series over our interval of convergence. That's all that absolute value of x less than 1 is hinting at here. And in fact, if we know this series, 1 over 1 plus x is equal to, if we know this function 1 over 1 plus x is equal to this series, and we want to figure out what the series is for the natural log of x plus 1, what we can actually do now is we could integrate both sides with respect to x. Now I know the integral of 1 over 1 plus x dx is natural log, and since we're representing this as a series, there's no need for us to put absolute value. We're talking about a series, which means we are always going to have positive values for x here anyways, for the numbers that we are plugging in. So now on the right hand side, we can integrate each term. So that's going to give me x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus dot 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 plus c. So eventually this is still going to be infinite, but we still do need to have a constant in there. And actually what I typically like to do instead of writing c at the end is I like to write it over here at the beginning so that I can still show that this series is still infinite. But in this particular case, we know about natural log, so let's go ahead and solve for c. Let's use the fact that we know that natural log of 1 is equal to 0. So we can use the fact that when x is 0, the function is also 0. Sorry, that's an ugly 0, 0. Let's use this point 0, 0 to solve for c. So think about what's happening here. Natural log of 1 plus 0 equals c plus, and then what's happening to every single one of these terms? They're all 0. We're plugging in 0 for x, 0 minus 0 plus 0 minus 0, etc. All of those terms are going to be equal to 0, so we can find out that c is in fact itself 0. So we can use what we just found out c is to write natural log as a power series. We can even come up with a general term, which would be negative 1 to the n times x to the n over n, and then it is infinite, is going on forever. So I'm out of space, but I want you to think about, we just found a power series for natural log of 1 plus x, but could we find a power series for just natural log of x, using what we know, what we have just figured out, to manipulate this power series up here in blue to find natural log of x. So go ahead and pause the video and see if you can find a way to adjust natural log of x plus 1 to figure out what natural log of x is. So you should be asking yourself, how is natural log of x different than natural log of 1 plus x? And I know that seems like a silly question, but how is it different? It is minus 1. We're subtracting 1. So negative 1 plus that 1 plus x. So instead of taking natural log of 1 plus x, we're taking the natural log of negative 1 plus that, because if I simplified inside parentheses, I would get natural log of x, and that is in fact what we are interested in. So how does that affect the power series? So in order to use substitution, what I want to do is I want to make it still look like 1 plus x. I just want to substitute something else in for x. And that's exactly what I'm going to do. So I'm going to rewrite this. I'm going to rearrange this. I'm going to flip-flop my 1 and my negative 1 so that in parentheses over here I have x. Ooh, that's a hard to read color. I have x minus 1. So basically what I'm doing is I'm letting x equal x minus 1 so that if I simplified this inside, I would get natural log of x. So what does that mean for our power series? It means that we're going to substitute x minus 1 in for each of these x's. So instead of the first term being x, the first term is going to be, I'm going to come down here, x minus 1. Instead of the second term being minus x squared over 2, it's going to be x minus 1 squared over 2. Plus x minus 1 cubed over 3 plus dot dot dot. And we could even adjust our general term. I'm running out of space here. So negative 1 to the n times x minus 1 to the n over n plus dot dot dot. So pause the video, make sure that you have all of this down, and then we're going to work through some examples and just get an idea a little bit more of how we can use this. So go ahead and pause the video, get this down, and then unpause the video when you're ready to look at these last 4 examples. So go ahead and take a look over 4, 5, 6, and 7. And if you are looking at those 4 and you're thinking, I think I could handle this, then go ahead and pause the video and see how you do. For example, number 4 is just asking you to take the derivative. So if you're looking at g of x and you're thinking, I could take the derivative of each of those terms, no problem. Then go ahead and pause the video and do that. If you think that you're going to get stuck on one of those problems, then you can follow along with me. But it is great for you to try and work through some of these on your own. So number 4, g prime of x is going to be 0, which I'm not going to write, minus 2x over 2 factorial, plus 4x to the third over 4 factorial, minus 6x to the fifth over 6 factorial, plus dot, 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 plus our general term, negative 1 to the n times 2n, x to the 2n minus 1, all over 2n factorial plus dot, dot, dot. Let me rewrite that so it fits better. And I'm just going to simplify this a little bit. So this is equal to g prime of x is going to be equal to negative x plus x to the third over 3 factorial minus x to the fifth over 5 factorial plus dot, 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 plus negative 1 to the n x to the 2n minus 1 over 2n minus 1 factorial plus dot, dot, dot. Number 5 is asking us to write an equivalent power series. So what we can do is we can use what we know about 1 over 1 minus x. So in this case, our r value would be x to the 4th. So this is really equal to the integral of that power series, 1 plus x to the 4th plus x to the 4th squared plus x to the 4th to the 3rd plus dot, dot, dot. Since it's not asking me for the general term, I'm not even going to worry about the general term on this problem. I do think I have it on my worked out notes solution if you want to check it out there. So all I did here was I let a is 1, r is x to the 4th, and I wrote that power series, and we're going to integrate that power series, and we can integrate each of these terms. That's going to give us x plus x to the 5th over 5 plus x to the not 8. That would be 8, and then we add 1 to get 9 over 9, plus this would be x to the 12th, so x to the 13th over 13 plus dot, dot, dot. I will put the general term here just in case you're wondering, x to the 4n plus 1 over 4n plus 1 plus dot, dot, dot. Now, if you haven't done any of these problems on your own, I really recommend that you pause the video and try and do number 6 on your own. So number 6 says, use the derivative of a known power series, f of x, to find a power series for g of x, and that is 1 over 1 minus x quantity squared. So let's let f of x equal 1 over 1 minus x. And we know that this power series is just 1 plus x squared plus x to the 3rd plus dot, dot, dot. And now I want you to think about, how is this f of x I just created related to g of x? Well, if you think for a minute, g of x is actually just the derivative of f of x, which means that I can take the f of x that I just represented as a series, and I can take the derivative of each term to get my g of x. So this would be 0 plus 1 plus 2x plus 3x squared plus dot, dot, dot. And again, these problems aren't telling you exactly how many terms you need to have or whether or not you should have a general term. This original f of x, that general term is just x to the n. This one, so if I took the derivative of that, that would give me n times x to the n minus 1, if you want to add the general term on there just for practice. But if I don't ask you for a general term on a problem, don't write it, because if you incorrectly write it, you're forcing me to take off a point on something that I didn't actually want you to do. So make sure you're paying close attention to the directions, because if you're not asked about a general term, you don't have to list it. All right, last question in 7.4. Use your result from number 6 to find a power series for h of x. So I want to ask myself, since I know I'm going to use the part that I just used on number 6, how are these related? So I'm going to note that g of x g prime of x, if I take the derivative of g, that does not look like a prime, let's try again, g prime of x would be, what's the derivative of 1 over the quantity 1 minus x squared? Well, that derivative would be 2 over 1 minus x to the third power, right? Well, it would be negative 2, but then I would also multiply that by a negative. So now that my denominators are the same between g and h, or between g prime and h, I want to find a way to relate them. So h of x is really just the same thing as 1/2 of g prime of x. So we have g of x here, over here. So g of x is, I'm not going to do the general term on this one. I am going to do 4 terms though, so what would this next term be? 4x cubed, which means that g prime of x, let's use a different color here, g prime of x would be 2 plus 6x plus 12x squared plus ... And h of x is 1/2 of that, so we want 1/2 of g prime of x. That's going to give me h of x. 1/2 of 2 is 1, 1/2 of 6x is 3x, 1/2 of 12x squared is 6x squared. And I think that you're getting the idea here. And we could, again, write a general rule if we really needed to. So, key things in this section, 7.4 part 2, using this idea of a power series and taking what we know about a power series to relate it to different functions. A big idea in this particular section was the fact that we can integrate and differentiate a power series in the same way that we integrate and differentiate a polynomial using the power rule, which is incredibly helpful because, again, we love polynomials. Polynomials are super crazy easy to integrate and differentiate. We love polynomials. We can use power series we have seen so far to define more complicated functions like e to the x and natural log of x or natural log of x plus 1. And that might be incredibly helpful, and we're going to extend and see why that's helpful in future sections. So make sure to write down any questions if you have them, and I look forward to supporting you on this in class. Thanks for listening.